Good morning, all of you. Electrochemistry lesson. In that one, the first part has been finished. Electrochemical cells, and then there the theory part as well as the all the formulae related to them, the different models, previous questions, our Chaitanya material exercises, all are finished. Now the next second part, the second part. See, in electrochemistry lesson, what and all you will study. First one, the electrochemical cells. The next one, conductance, right? Conductance. And then, see, after that, Faraday's laws. Lastly, batteries. These are the concepts we are going to study. So now, the next part, conductance of electrolytic solutions. See, the second part one, that is conductance in electrolytic solutions. This is the heading. Conductance in electrolytic solutions. Let us discuss about them. This is purely theory part, actually. Theory part. And then completely related to physics. Just see, with respect to the chemistry, what are the important points? Those we are going to discuss. Okay, so now let us take them. And then in this one, what is the important? So just the terms, what are the terms important for us, as well as the formula related, as well as see the units, because they may ask you about the match the following model question on that. That's right. Okay. So now the first one, resistance. Okay. So now the units now we can have separately like this. The units. The first one, resistance units. That is ohm. Ohm. Resistance is okay. It is mentioned in ohms. Resistance. See, the resistance, it is directly proportional to length of object, and then inversely proportional to cross sectional area of that object. So therefore we write like this: R is proportional to L, length of the object, and then A, area of the object. That is. So therefore, now the length means meters, centimeters, area meter square or centimeter square, like that we write. Is it not? Now this is proportional. So now say R is equal to L by A. Now here, what is this? The rho. That is, this is called as the specific resistance. The rho is specific resistance. I am saying, okay, that is, let me write that. The rho you can call as, see, the specific resistance or resistivity. What do you write now? This one is rho is equal to R into A by L. R is ohm. A meter square. L meters. Therefore, ohm into meter. Then what do you write? Ohm into meter. Otherwise, ohm into centimeter. The units will be like this. This is another one. Okay. This is one formula. Please remember that is. Okay. Then next one. So here the rho, that is proportionality constant, like this. See, now sometimes they will ask you the definition. The definition of the rho. So rho is equal to, what do you say? Resistance A divided by L. Is it not? That is. Therefore, what do you say? See, now the definition, suppose if they ask the definition, how do you write? Suppose, see, rho is equal to R into A by L. See, the rho, when can be it equal to R? When A is 1, L also 1. When A is 1, L also 1. Therefore, how do you define the rho? RHO, rho. How do you define? Very simple. It is the resistance offered by an object with 1 meter length with 1 meter square area of cross section. Okay. So the definition, if it is asked from the formula itself, you can define. How do you define, ma? So that is, how do you say? The rho is nothing but the resistance offered by an object, okay, which is 1 meter length and then having 1 meter square area of cross section. Like that you can say. So this is the definition. You can write like that. Is it not? Now another one. Another one. See, that is, let me take reciprocal of this equation. Reciprocal of this equation. Okay, that one. Suppose 1 by R. 1 by R. Reciprocal of the resistance. Reciprocal of the resistance. It is G. Reciprocal of the resistance is called as G. What is the meaning of G? G is conductance. G is conductance. Then see, what are the units? 1 by resistance now. 1 by resistance. So ohm inverse. Otherwise mho. Otherwise symbol ohm inverse or Siemens or Siemens. Yes. Yes. That is Siemens. It is. You can say. It is the way you can define. Siemens or Siemens. Yes. The conductance, the units will be like this. Then next one. Next one. Rho. Is there none? So 1 by rho. So K. Kappa. Kappa. K. Kappa. That is, K means the specific conductance. So the K, you can say, see, specific conductance. Specific conductance or conductivity. Conductivity. So therefore, it is nothing but 1 by rho, 1 by rho, 1 by rho, 1 divided by rho. This is. That means ohm inverse, meter inverse. So what are the units? Ohm inverse, meter inverse. Ohm inverse, say centimeter inverse. Otherwise, say ohm inverse means Siemens per meter. Siemens per centimeter, like this. Per meter or per centimeter, like this. These are the units for specific conductance and those. Then here only one more formula. One more. L by A is there, na? L by A. L by A is called as G star. L by A is G star. G star. So G star here, G star, that is cell constant. Cell constant. What are the units? G star means length by area. So therefore, centimeter inverse, meter inverse. Centimeter inverse, meter inverse. That is centimeter inverse, meter inverse. Okay, that is the G star. G star, that is. Okay, like that. So this is another formula. Yes, then next one. Now, suppose reciprocal of this one. Reciprocal of this one I am saying. The reciprocal of this one. So, see, suppose 1 by R, 1 by rho, 1 by L by A. 1 by L by A, that is. So what is 1 by rho? What is 1 by rho? That is 1 by rho is K. That is K. Then 1 by rho. 1 by R is G. 1 divided by this, it goes to this one, numerator. So G star. So this is another formula. So please remember, these are some important formulae related to conductance now. Conductance. Understand? So especially you please concentrate on units. Sometimes they will give match the following model. Match the following model on this. Remember that is. Please remember. This is another unit. So, okay, the next concept one, conductance in electrolytic solutions. We are going to take conductance in electrolytic solutions. Come on, you please, you take the screenshot. You take the screenshot. Yeah, I am going to rub it, ma. See. So please remember all this. Remember all this. See, the conductors. We know that, see, conductors are two types, electronic and then electrolytic conductors. Electronic conductors means the metals and its alloys. The electronic conductors means metals and their alloys act as the electronic conductors. Is it not? So, yeah, see, about them, it is purely physics. So in physics, you will discuss about that. And then there only one term, superconductor. Superconductor. What is the meaning of that? Otherwise, to be a superconductor, what is the condition? To be a superconductor, what is the requisite condition? Very simple. That is zero resistance. The superconductor means zero resistance. Zero resistance. One thing, resistance, the see metallic conductor or electronic conductor. See, the meaning is conductance due to the movement of electrons. That is, hence it will be called as electronic conductor. Electronic conductor. So see, in the electronic conductor, see, the metallic conduction and temperature, how they are related. There, see, when we raise the temperature, resistance also increases. Resistance also increases. But what I am saying, superconductor means zero resistance. That means what it should do? Temperature should be decreased. Therefore, temperature. Then, see, they have developed some metals and some alloys also. They have gone to a temperature 0 to 15. 0 to 15, 15 Kelvin. That means what is the lowest possible temperature? Lowest possible temperature. Lowest I am saying minus 273 degrees Celsius. Minus 273 degrees Celsius It is the lowest possible temperature. Otherwise, 0 Kelvin. 0 Kelvin. It is the lowest temperature possible. Lowest temperature possible. Therefore, see, that temperature, I am saying, temperature, that temperature, you can expect zero resistance. So scientists, they have prepared metals and their alloys at a temperature of 0 to 15K, 0 to 15K, I am saying 0 to 15K, and then they obtained superconductors. Whereas after that, what happened now? They have synthesized some polymers. So those polymers act as superconductors. 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 Even even at a temperature of 150K, 150K, 150K. At that, little bit high temperature only, somewhat. Of course, even it is minus only, but anyhow, at that 150K means somewhat a great improvement. So the scientists, they have made by that. And also one more thing. See, around 2001, 2002, actually in our India, in the year of 96, 95, like that, mobiles are introduced into the market. Mobiles, right? When they came to our Ballari city, and then the cities like this, in the year of 97, like that, 97, 98, like that, they have been entered into the market. But anyhow, see, at the time, the mobile, do you know the mobile, how much big it was? This much big actually. Just like a cordless telephone, that much big one. Okay? So we used to hand to the right, and then we will be carrying like that, nearly, more than, of course, nearly 1 kg, like that. Why? Because at that time, the battery itself very heavy. Battery was very heavy at the time. But whereas, the battery in the sense, at that time also, what happened now? The metals and those only can act as the conductors, like that they were thinking. But whereas, when the polymers were discovered, of course, in the year of 2000, 3 scientists, actually, they discovered a polymer, plastic, which is a very good conductor, almost the equal to metal. So when compared to metal, the polymer will be elastic, flexible, right? Flexible, and then very light, very thin also. Therefore, the polymers, a great invention, that is great invention. Just because of that, the mobile size enormously decreased. Nowadays, the mobile, how much ever thin it is costly and stylish. Is it not? They are becoming very thinner and thinner. Of course, by next year we are going to expect the foldable also. That means excellent one. Nowadays, of course, Motorola and Samsung, they have released, but anyhow, that is in starting stage only. But even though they are costing about 1 lakh, more than 1 lakh, right? But whereas next year like that, still more in cheaper way, we are going to get that folder. So whereas in a small one, just like a mobile, when it is opened, it is a tab. It is a tab, that is. Okay. So because when will be possible? Whenever the battery, the inside the battery is very small, and it should have a high capacity. That is also most important. Please remember, high capacity also, that is. So like that, the plastics are like that. So the plastics, they have changed our lives a lot. Without plastics, we can't live. Without plastics, we can't live. I am saying everything is plastic world. Plastic means polymers. Polymers. I am saying. Okay. See now. See the metallic conduction. Now we don't discuss in our syllabus because it is not there for us. It is purely physics part. In physics, that will be discussed. Now in chemistry, we discuss about conductance in electrolytic solutions. Electrolytic solutions. You consider the water. Consider the water, I am saying. So in case of the water, that is, see, one important point is there, man. That is, please mention. See, at 25 degrees C, at 25 degrees C, the conductance of water, water that is found as, see, 3.5 into 10 power minus 5 Siemens meter inverse. Okay, Siemens meter inverse, that is, please remember, that is. Okay, so therefore, the conductance, that is, you can say conductivity, you can say, that means the K value, you can say K, the specific conductance or conductivity. Please by heart that value. It is given in the textbook, you have to by heart it. You have to by heart it, I am saying. Understand? So therefore, this is an important one. Then next one, another one, important one. See, conductivity, conductivity of electrolytic, electrolytic solutions, electrolytic solutions depend on, electrolytic solutions depend on, see, some important points are there. The nature of electrolyte added, the nature of electrolyte added, the nature of electrolyte added, size of ions produced and their solvation. Okay, size of ions produced and their solvation, that is. Then the nature of solvent, solvent and its viscosity, nature of solvent and its viscosity. So please see the third one, the nature of solvent and its viscosity. Last one, important one, temperature. Temperature. So here temperature directly proportional. Directly proportional, I am saying. Directly proportional. Remember, directly proportional. So conductivity of electrolytic solution depend on the number one, the nature of electrolyte added, size of ions produced and their solvation. Because okay, the next one, the nature of solvent and its viscosity, temperature. See here, the nature of electrolyte added, more ionic or less ionic, size of ions produced and their solvation. See, the ions, their size is also most important. Suppose if the size is heavy, it cannot move, right? Therefore, the conductivity will be low. Conductivity will be low. So that is depends on solvation. Because suppose, for example, suppose a particular ion, if it is solvated more, if it is solvated more, that means it will be carrying so many, it will be carrying so many water molecules. Therefore, it feels very heavy. Therefore, it moves slowly. It moves slowly. That is, remember. Then The nature of solvent and its viscosity. The nature of solvent and its viscosity. So that is also most important. If the solvent is viscous, therefore the ions will not move fast. That is it not? The next one, temperature. So if temperature is increased, ionization increases, and therefore, so more conductivity you will find. More conductivity you will find. That is. Okay, so this is another important one. Now these points important one in the form of statements, they can be asked in the form of statements. I am saying in the form of statements, you can note down, you take the screenshot for that. Yes, next one, another one. See, molar conductivity. Molar conductivity. Let us take them. Molar conductivity. That is another important one. See, molar conductivity is denoted by lambda m. Lambda m. Now here only for lambda m, some important formula. K by C. K by C. Yeah, you just go through that formula. Go through that formula now. Now here lambda m, Siemens, okay, Siemens meter square per mole. The units, please listen. This is an important formula. They used to ask in our regular PU. Okay, the units are important. So Siemens meter square per mole. Next, this one K. Siemens per meter. Next, concentration. It is concentration. The concentration is moles per meter cubed. Moles per meter cubed, like that. In that way you should take. Understand? So lambda m, it is the way. So therefore, when you want to use this formula, lambda m, molar conductivity will be obtained like this. And then K, Siemens per meter. C, concentration, moles per meter cubed. Generally, concentration we don't take like this. Remember, we never take like this. But anyhow, in problems, if they want to confuse you, they may give in this way. So now, next one, another one. Let me take like this. Lambda m, it is equal to K into, that is K into 1000 by m. This is another one. You please just see, that is now here Siemens centimeter square, mole inverse. K, Siemens centimeter inverse. Molarity, moles per liter. Remember. So this formula again, remember now, like this. Okay, and then 1 Siemens meter square mole inverse, it is equal to, how this is related to Siemens centimeter square mole inverse. How it is? 10 power 4. That is 10 power 4. That is. Okay. Otherwise, 1 Siemens centimeter square mole inverse, it is equal to 10 power minus 4 Siemens meter square mole inverse. It is the way, that is. So in that way also you can, that is. So please remember these two formulae. Okay, this regularly we will be using. This we will be using regularly. That is, please remember this is. Okay, so this is. Then now see, based on this we will be doing. And also one more thing. Remember how they will be converted like this. The see SI units, CCS units, SI units and CCS units. Okay, remember. So now take the screenshot for that. Yeah, I'm going for a bit more. See that? So now, see how molar conductivity and then the concentration, how they are related, So the graph on graphical representation is also there. Graphical representation, we can discuss about that. Okay, see the molar conductivity, the molar conductivity versus concentration. Concentration. So here, how do they take lambda m versus root c? They take root c because after so many observations, they observe like this. After so many observations, the relation is like this versus root c. That is. So now a strong electrolyte. See, strong electrolyte. I am saying strong electrolyte means which ionizes completely. KCl, NaCl, NaOH, like this. All these are the strong electrolytes. So, like this, lambda m, and then root c, that is. Now here, the graph will be like this. Linear graph, negative slope. Linear graph, negative slope. See now, here only important thing. When we move from here to here, x-axis. On x-axis, we have taken concentration. On x-axis, we have taken concentration. Is it not? So, if you move like this, concentration is increasing. Like this, concentration decreasing. So, decreasing concentration means, what do you say? Decreasing concentration means, you can say like this, that is, decreasing concentration means, you can call as dilution. Decreasing concentration means, it is called as dilution. Dilution, that is. So, dilution, that is, you can call like that. dilution. So now in this one, see, if you move like this, it is a dilution. With the dilution, what is happening? Lambda m is increasing. Is it not? Lambda m is. So what you can say? Lambda m increases with dilution. Dilution means like this one, like this. It is increasing. So therefore, now extrapolation of this graph. Extrapolation. This is called as. This is lambda naught m, not lambda naught m. So on y-axis, I have taken molar conductance, right? So the graph, it is extrapolated, is it not, to the y-axis, and then there you can call that one as lambda naught m. See, lambda naught m, what do you say? That is, see, you call that one as molar conductance at infinite dilution. Infinite dilution, you can call infinite dilution. What is the meaning of infinite dilution? What is the meaning of infinite dilution? So infinite dilution means, see the meaning, let me take like this. Infinite dilution means 100% ionization. That means alpha is 1. Alpha is equal to 1. Alpha is equal to 1. 100% ionization, 100% dissociation, and alpha value is equal to 1. That is. So that is for say the strong electrolyte. Strong electrolyte. Yeah, there only say one formula, one equation is there. Lambda m, it is equal to lambda naught m minus a square root of c. Square root of c. So therefore, here, what same, this graph only you will get it. So it is the way, right? So lambda m, this is square root of c root. That this is intercept. What? Intercept. So therefore, this is intercept. Intercept value is how much, huh? Lambda naught m. Then what about the slope? A negative slope minus a. That is minus a. That is. Remember, the graph also important. Okay. So it is the way you will discuss about that. So in case of strong electrolyte, how do you calculate? Lambda naught m? Very simple. Say you have to draw a graph. Extrapolation. You will get a graph like this one. Just extrapolation towards y-axis. Therefore, it will get lambda naught m. You will get lambda naught m. It is the way we get that. So remember, it is the way I am saying. So this is about strong electrolyte. Yeah, come on, take the screenshot for that. Take it. Okay. So now lastly here, see, weak electrolyte, lambda m, right? Square root of c, okay? We get like this. So that will be, see, this is like this. For example, CH3COOH. So in case of weak electrolyte, extrapolation is not possible. In case of weak electrolyte, Extrapolation is not possible. So how to calculate molar conductance at infinite dilution? Molar conductance at infinite dilution is also called as limiting molar conductance. See, one more name you can give limiting molar conductance. Limiting molar conductance for this. You can give that name. Okay. So it is the way how that is. So now for strong electrolytes, the graph like this. This is the way we can. For weak electrolytes, how? That is the problem. Is it not? So again, on Monday, we will discuss about that.